Good afternoon, ladies and gentlemen. This is Mark Wu, and welcome to my MassMotion webinar. First of all, let me introduce the background about modeling the fire evacuation in road tunnel. Fire in road tunnels can be catastrophic. Disasters fire, Mont Blanc fire, 1999 claimed 39 lives, and investigations on those major tunnel fire highlight the shortcomings in human behaviors during the fire evacuation. Since then, modeling the human behaviors in tunnel evacuation has become an important topic for fire engineering. It led to the establishment of design regulation at a worldwide level in order to improve the user protection, and that includes the well-known EU directive. Nowadays, computational simulation, including our agent-based MassMotion, is becoming a brilliant tool for safety analysis in modern fire engineering designs. Surprisingly, research using this approach is limited, particularly for British road tunnel. So this project would provide us a great opportunity to improve tunnel safety. Now, I'm going to present you a methodology of an agent-based, scenario-based risk investigation. Our case study concerns the fire evacuation in the Dartford Tunnel, one of the key highway corridor in the UK. We'll first discuss at the main aspect of behavior modeling and see how we can validate them. Then, for the first time, we'll use the agent-based MassMotion in such investigation in order to outline the key safety indicators. It will lead us to discuss the recommendations to optimize the current evacuation procedures. Finally, we'll summarize the design methodology for future projects. So, why Dartford tunnels? It is the busiest London road tunnels. It carries over 75,000 northbound vehicles a day, more than any other London road tunnels. Clearly, a fire at this key corridor is likely to bring life loss and great economic damage. Therefore, a risk investigation on its current evacuation procedure is important to provide maximum protection. To select the critical safety scenarios, we need the information about the past fire events. However, given the sensitivity of the information available, data on vehicle collision is instead referred to identify the incident likely locations. It is an appropriate assumption as the vehicle collision contributes to over 75% of the major tunnel fires globally. Most of the incidents occurs inside the tunnel at locations of 400 and 750 meters inside the tunnel. For this demonstration, I will use the possible worst-case scenario at the 750-meter location, where we expect the longest evacuation distance, but also the longest evacuation time that may be required. When fire occurs, tunnel entrance is expected to be closed within the first 3 minutes. Depends on the day period and how much traffic we get at that time. We consider 4 different scenarios, and they all have different lengths of vehicle queuing inside the tunnel behind the fire spot, as you see here. On the other hand, the traffic share between the car and heavy goods vehicles is about 10 to 1. Consider the Dartford Tunnel is a very important truck corridor. It is important to model the presence of AGV here. Now, we assume all cars, vehicles are accumulated in a regular compact format as so. They all remain stationary throughout our simulation. Furthermore, ventilation systems operate northbound to create a smoke-free evacuation area, so it ensures no visual impairment among the evacuees. Normal procedures requires evacuation via the south entrance. Under special circumstances, cross-passage facility may be used to reach the adjacent tunnel, and evacuees may leave from there. With the tunnel features and traffic data available, the 3D models is then constructed in the Google SketchUp before being imported into the MassMotion. Here, as you see, is the 750-meter tunnel section model. Another special about the Dartford Tunnel, it's a complicated geometry. It is a 1,430-meter long tunnel, twin-sported, and it features two high-rise sidewalks, as you see here. Each of them is 1.1 meter above the ground and 0.9 meters wide. The ladder access to the high-rise sidewalks, as you see here, is about 50 meters apart from each other and available inside the tunnels. Under the current traffic condition, we expect many vehicles and occupants may be affected by the evacuation. So the sidewalks may be used as an alternative route to avoid the congestion on the road surface. Our models consider the evacuation because of one of the twin spurs. The cross passage, highlighted in orange, connected between the sidewalks of two adjacent tunnels. Furthermore, vehicles in our simulation is modeled as a 4.5 meter times by 2 meter hollowed barrier section. The origin of agent movements here, called seat, are inside of individual bits. It's meant to mimic the realistic movements of people to start the movement from inside the cars, open the door, and evacuate towards the safety exit, which is here, the tunnel exit. Again, the evacuation area, as you see, we expect to be very confined and highly occupied. So the corresponding evacuees' behavior need to be understood and carefully modeled. Traditional behavior modeling considers the human behaviors to perceive and react to the environment before they actually commit to the evacuation. This decision-making process is a continuous phenomenon during the entire evacuation procedure, but highly associated with individual characteristics. Hence, we want to use different modeling techniques to capture these differences and so model the realistic crowd dynamics. The most interesting parameter to look at is the pre-movement times. It is indeed an influential factor to the overall evacuation time required. Initially, only the drivers in front of a queue encounters and observes the obvious danger of fire. That means flame, smoke, and heat. So they detect the danger and decide to retreat and leave the tunnel earlier. These actions then become a significant source of social influence, particularly in these commonly unfamiliar surroundings. And so it will initiate the group evacuation of most of the normal drivers left behind. Unfortunately, there will be a small number of occupants situated far behind the queuing may receive less cue about the danger, because they won't see many things go wrong around them. So they would evacuate much later in the process. As you see, this wave pattern of extending evacuation time can be best generalized by a normal distribution, ranged from 30 seconds to 210. The parameters were then tested to ensure each agent would behave realistically in the simulation. As no verified data on fire evacuation from the Dartford Tunnel is available, they were validated by using results from a behavioral test of evacuation, which conducted in the Benelux Tunnel, Netherlands. Let's have a look at the validation model itself. A similar scenario, as you see here, compared to the one we had in the Dartford Tunnel is considered. This situation was injected at a mid-tunnel section with a similarly compact vehicle accumulation behind. all evacuees react to the situation within the expected range of pre-movement times. That's mean we mentioned 30 seconds to 210. They all start their movement from inside of vehicles. See here. And all move towards the nearest safety exit available. This means, as you can see, this and here. The first experiment is to implicitly input the agent properties. Here we are talking about the origins, the pre-movement times, and the evacuation, the pre-movement times they had, and of course the individual file. That means the body radius and the speeds they had. And also we assume they remain constant throughout the evacuation process. The second model we use is to use the probabilistic modeling on agent properties. Here we introduced a normal distribution on pre-movement times, minimum 30 seconds, maximum 3 minutes and 30 seconds. That means 210. Mean is 120, and standard deviation is 30 seconds. The exit is said to be these two, the two that we mentioned, the safety gate. And of course, we also introduce a default value of normal distribution with a minimum 0.65, maximum 2.05, mean 1.35, and standard deviation 0.25. So let's have a look. So let's have a look how the evacuation will looks like. So make it a bit faster. They will start to move. They move out from the individual cars, and they will see where the least congested and most close and nearest route to reach the exit. Individual evacuation time will be recorded once they reach the safety exit. So here we are. By implicitly input the individual characteristics, that means the pre-movement times, agent locations, but also velocity. The MassMotion model indeed reproduced the original individual evacuation time, and that's also within the satisfactory range of error of 7.3%. It certainly suggests that the movement algorithm is consistent to mimic the realistic crowd movement. On the other hand, the probabilistic modeling predicts a slower individual evacuation time, as you see here. The 10.7% modeling uncertainty is due to the nature of stochastic modeling. It is, however, affected by the number of simulations that we executed. Here, by having additional 20 simulations, the increment on goodness of fit suggests a clear improvement on prediction accuracy from 0.00067 to 0.00885. The generated 10.7% error on predicting the total evacuation time is acceptable in other validation projects of MassMotion. Here, without further simulations, the selected parameters is confirmed to be appropriate for our behavior modeling of tunnel evacuation later. Now, we have our parameters ready for the inputs. In this project, the following scenarios were evaluated, simulated, and the results are collected. Firstly is a control experiment. It models the ideal evacuation, when all evacuees start to evacuate immediately without hesitation. In other words, pre-movement time equal to 0, and they will move with a relatively same speed and constant 1.35 meter per second. A second experiment models a normal evacuation. Here we employ the distribution law of various pre-movement times and speed, which varies from person to person. So the actual evacuation time is expected to be much longer. This increment is also believed due to the level of congestion evacuees experienced, as the movements are interfered and slowed down. So in the third experiment, as I mentioned before, all evacuees are modeled to use the sidewalks to avoid the congestion on the road surface. Interestingly, the simulation has indicated its increasing congestion and resultant time delays. In other words, the higher level of congestion they experience, the longer the evacuation time may become. To show where congestion may occur, let us have a look at the experience density map distribution in the MassMotion. Generally, people tend to choose the widest and least congested route to evacuate. This means here, which would be the mid-tunnel routes. In real evacuation, the resultant crowd dynamics would conflicts with the stationary vehicles at the bottleneck, and therefore contributes to the localized congestion, as you see the reddish spot here, here, and here. When switched to the sidewalks, the approaching evacuees cannot overtaking the slow marching company in front of them, particularly on the narrow 0.9 pathway. Therefore, the additional congestion will be introduced. Eventually, this unidirectional evacuation flow would overcome the ramps area near the entrance. It magnifies the congestion towards the end of the evacuation process. Furthermore, many real experiments report other sources of congestions. Evacuees may stop during their movement to seek for extra safety information, such as readouts from the emergency signage. The stationary bodies can block others' movement, so the congestion may occur. From the driver's point of view, they sometimes execute the so-called U-turn driving to try to go around the queuing in front. Occasionally, it may cause additional secondary collision, which would block the entire road space completely. The congestion is often used to evaluate the user experience and system efficiency on the certain pedestrian density. The delay, as a result of it, increased the threat on evacuees of being caught by the quickly spreading smoke, particularly in the tunnel evacuation scenarios. Because the time and safety resource is very limited, it may also bring unnecessary stress among the evacuees. The potential resultant excessive behavior, such as stampede or overreactions, would cause further casualties or injuries. Here is some real observation during a real evacuation in the Dartford Tunnel 5 years ago. Initially, people chose the mid-road and the least congested road to walk before they encountered the reckless U-turn driving and forced to go around. Later on, the evacuating cameramen were seen by other occupants. They start to realize the problem, they start to evacuate, and it leads to congestion on the road surface. We have seen these safety issues earlier in the MassMotion simulation. That means how people choose the route, how a factor of social influence may affect the individual decisions, and how congestions can affect the evacuation dynamics. In other words, our recommendation should aim to reduce the individual evacuation time, and that can be done by reducing the level of congestions. So let's have a look how we can do the mitigations. Here is the evacuation scenario for the sidewalks evacuation. we introduced we put two barriers act as secondary collisions at the end of queue to block the entire road surface. So we use this to force the agent to use the sidewalks via the nearest nearest ladder access. Remind that the first problem we had is insufficient walking space on the sidewalks. So here we recommend a mechanism of overtaking island that you see here. So let's just run the simulations. I suggest it to the ROS level to see it more clearly. Save this. So let's run the simulation. And right now, there's still all the evacuees. They start to realize danger. They start to evacuate because they can't leave via the road surface, so they have to use the ladder to get onto the sidewalks. See here, and they all move towards the assigned exit, which is the tunnel portals. Soon you will see they start queuing. They start to see the queues. Let's just slow down a little bit. For example, here, see these queues. And when they get onto the overtaking island, the extra walking width allow the evacuees behind can overtake the slow marching company in front and carry on with a relatively higher speed of evacuation. Also, you can see here, they start to move around, find the free space, and carry on with the movement. Let's have a see the density map of this analysis. You can clearly see a dissipation of the evacuation flow once they get onto the overtaking island. So it certainly suggests that congestion is indeed reduced. Of course, consider the width expansion for the entire tunnel here is going to be highly expensive. I proposed several of OT island installation to ensure the slow marching company, the queue can be completely dissolved and disintegrated. That means if you see on the crowd here, it will be less overcrowded. The queuing actually is still there, but obviously going to be much shorter. And of course, and also there will be a sufficient headway among two of them. So this is the first strategy we proposed to use the overtaking island, and this is a passive control strategy. The second plan we use is to run a cross-passage evacuation. Again, let's speed a little bit. So this window here is for the cross-passage 1, and this is for the cross-passage 2. You see here. The alternative exit allows a two-way evacuation. That means to divert the flow on the portal directions. Let us see the density maps again. So cross-passage operation, as you see here, they makes the evacuee situate further behind the tunnel. For example, this part, don't need to travel all the way up to the tunnel entrance. So they can just choose the nearest exit where possible to leave the incident impacted tunnel. So lots of reddish color will be disappears as if we compare to the density map of a normal evacuation. You clearly see a change that but of the reddish part is actually disappears, which shows a magnificent reduction on congestion duration. Are they actually working to reduce the total evacuation time? The answer is definitely yes. Here, by alleviating the congestion to using the overtaking island, reduce the evacuation time for over 75% of the evacuees. This is because with less congestions, they can work with a much higher speed, so they can reach the safety exit much earlier. On the other hand, the active controls using the cross passage further reduce the evacuation distance for evacuees to reach the nearest exit. So here, the decreasing on evacuation time is considered to be a coupling effect of congestion reduction and distance reduction together. Both the passive and active crowd control strategy are highly effective. Application of cross passage would deliver a remarkable reduction on average congestions by up to 75.5%. In many cases, it will certainly optimize the current evacuation plan in terms of alleviating the congestion. So we believe it's going to reduce the evacuation time required. It is important to have this additional safety time, resources, and exit available. It would help us to create a calm and safe evacuation order. So far, this project has shown you how a designed fire safety strategy can be evaluated and designed in a systematic manner. We first revised that the analysis requires to consider a range of safety scenarios. It should generalize the key safety features, the traffic features of the tunnel, its geometries, as well as its current safety procedures. It then gives us the confidence to select and model the appropriate behavior factors. It must cover the following three stages of human decision-making process, essentially perceptions, reaction, and the movement. To validate them, this project chooses the appropriate validation scenario from the result of a behavior experiment. Based upon this scenario-based simulation strategy, the results show how congestion level service can actually influence the individual evacuation time may required. The comparison among them allows us to identify the critical safety issues. And so we can make the corresponding recommendation to tackle these problems. The outcome of this modification on tunnel geometry and safety procedures can be previewed, so we can make further analysis and justice on its designs. Of course, a major uncertainty introduced to simplify a real fire evacuation situation is we omit the influence of fire dynamics. It's mainly due to the current missing input available in the MassMotion version. As we previously addressed, the couple effects of rapid heat and smoke dissipation in a confined tunnel space can physically disrupt the perception of the occupants, and so distort their decision-making process. Therefore, a collaboration with other validated models is recommended to help to model better evacuation behaviors. As a result of it, we'll be able to get a more realistic evacuation dynamics. In fact, it actually brings another interesting extension to this project. That means we can introduce the potential risk indicators such as available evacuation time, ASET, to conduct a more quantitative analysis, QAS. Hence, further sensitivity tests will be able to obtain more results and help us to refine the previous proposed modifications. Overall, this continuous effort at improving the model reliability is critical to the understanding of the resulting human behaviors. Most importantly, it formulates a long-lasting and robust safety strategy. To conclude, the project demonstrates a practical methodology of risk investigation for the tunnel evacuation procedure. By using the agent-based MassMotion, I have shown you how congestion causes delays on individual evacuation, particularly during a large-scale MassMotion. And I also show you how we can use the modification to alleviate them. Thirdly, we further agreed that the model can be refined in order to improve its prediction accuracy. In summary, we recommend this methodology proposed in this project to be used in future risk investigation. To bring this demonstration to the end, Adassus and I would like to take this opportunity to thank the Arab and the Oasis Department for their support during the duration of this project. Thank you very much for attending today. The script and resources will be made available online, and I'm looking forward to hear from you.